turn this off. Let's turn this off. All right, so so we have a word for this. Does anybody recall the word when something is kinetically stable but thermodynamically unstable, what that word is? I mentioned it before, but I don't know if anybody caught it. Starts with an N. We call it metastable. It's a metastable. Metastable means thermodynamically unstable, kinetically stable. Diamonds would be an example of metastable. Diamonds is actually the example I used a while back for this type of scenario. All right, but you have to recall that this practice exam, this was when thermal was chapter 19. And so we had talked about a lot more stuff by the time we got here. Now it's thrown down to chapter 13. A little different. And so the answer is none of the above. All right, what else were you uncertain about?
Number 2.
Number 2?
Yeah. It's not delta S. It's not like a trick for
It's not a trick question because why isn't it delta S? Why it isn't delta S is because we can measure absolute entropies. If this were Chem 1A, I'd ask you, can we measure absolute enthalpies? Absolute enthalpies would just be H, or absolute internal energy, U. We can measure delta H's and delta U's very easily, but what about H and U? You cannot, but S, you can, so this is different. These are absolute entropies here because we can measure these. Now, I spent some time talking about how they're determined, which is complicated. Deals with heat capacity measurements, that kind of stuff, and integrals and calculus. So, mentioned it, but the only reason mentioned it is because it's so different than H and U. And so just to illustrate that. And so those are S's, not delta S's. Was that the question?
Well, like, what if they were both the same state? Because I know, like, the higher entropy is usually the more.
What if they were both the same state?
Can it just be like a higher number in that scenario, or?
No. No, it's not deep enough. A little bit deeper than that. If they're both solids, then yeah, then you could say. If they're both liquids, if they're both gases, but if they're both aqueous, then you have to go deeper than that. Because you got to remember there are two scenarios when it's aqueous. It could either be the Did you guys have a chance to? This is better explained not in chapter 13. This is better explained in chapter 7. So let's go back there and take a look at chapter 7. In chapter 13, they just assume you already know it, kind of thing. And so let's go back to chapter 7 and take a look at this. Well, this one should be obvious. The standard enthalpy of formation is 0 for pure element in its reference form. And because the standard enthalpy of formation is defined for the formation of the substance from its elements in reference form. And so all these should have a delta H formation of 0. So for carbon, the most stable form would be graphite. The delta H formation would be graphite. We call carbon's reference form graphite, the most stable. And so diamond would have a slightly higher entropy. That's no different. This table is fine. This is a graphic illustrating what negative and positive delta H's formation mean. Then we want delta H's reaction. So we go on here. The question yesterday about this. And I skimmed through this because it's all pretty standard. And then we get to this section on page 278. It's only one page long. Let's see. Yeah, it's only one page long. And so what you should do, you know, if possible, is to just really understand just this one page. And that'll, I mean, that's where it originally was talked about, you know, this Appendix D thing. What's tricky about using Appendix D. And so page 278 talks about the problem that comes up when we're dealing with ion. What you can measure is you can measure the formation, or you can measure the reaction that forms both cation and anion. But if you were to do calorimetry, let's say we're going to form HCl, you can measure how much heat is involved in that, the formation of HCl, but really what you're forming are, you know, hydrogen or hydronium ions and chloride ions. And to separate that is very difficult. So here's where they're talking about this. So it's just 3 paragraphs, less than 1 page of writing. Know it, and then you'll see. So to answer your question, Eric, it doesn't depend on the phase because it could be aqueous, and then you have to subdivide aqueous into 2 categories. What 2 categories do you do? You do, let me just tell you, you do the cations versus the anions. The cations are all systematically going to be off one direction, and the anions are all systematically going to be off in the opposite direction. And so both of those are an error, but the good thing is when you add the cation with the anion, the systematic errors cancel each other out. If you don't have an anion, that's fine because it's already been canceled out in that sense, because eventually we would have to throw in the anion in there. And so it's not just phase, it's a little bit more. If you're dealing with solids, liquids, and gases, yeah, then you can divide it.
Both aqueous, do we need the cation?
I didn't divide it by phase, though. What did I divide it by? Because you could have H2O as a solid, liquid, or gas. And if you divide it by phase, then you're putting all the solids together, all the liquids together, all the gases together, and treating those separately. No, you don't do that. You divide it by, what, does anybody remember how I divided it by? Appendix D? Well, I divided by neutrals versus cations versus anions, and I called that, the neutrals were Kelvin, the anions I called Celsius, and the cations I called Celsius, and the anions I called Fahrenheit. I called the cation Celsius. You might have caught this or not caught this, but I called it Celsius because it kind of resembles Celsius in that you define 0 as being the freezing point of water, you know. Whereas Fahrenheit is a bit more tricky because Fahrenheit is 32 is defined as a freezing point of water, right? And it's kind of weird. Well, the same thing with the anions. If you wanted the anions would have been referenced, according to my discussion in lecture, would have been minus 167. And so the anions were referenced to minus 167, the cations were referenced to 0, and the neutrals were referenced to absolute 0. And so that's the brief nutshell review of what I talked about. But this is all in this one page here, page 278. So check that out. This page is critical, and I don't know, for this one page, I spent hours in Chem 1A talking about just this one page, and then maybe an hour in 1B. I'm talking about just this one page, so because it's so confusing, that's why. You want to know? I told you thermal was a struggle for me when I took thermal because I didn't know this stuff. I just used the numbers as is. So if somebody asked me a question like number, what was it? Number 2, I would have gotten it wrong. I would have gotten it wrong because I never learned this. And this is why thermo, the first test, I bombed the first test. I didn't know this stuff. It was a struggle. I was thinking, oh my God. But fortunately, I recovered by the time the final came. It was a midterm and a final, and the final saved me from a very bad midterm. Okay. All right. So that little definition. This is a one-page thing about the definition of this. Should know that. Or what else?
For number 8, you did it in class, and we got .032, but the one over here is .32, so is there an error, or is there another?
Well, I know I did it in class, but you should do it yourself, and you should say that, based on what you did, the answer should be, you should be confident.
Oh,
You should be-
I did it again. And
Yeah,
then
you did it again, and you should be confident that the answer is 0.032, not 0.32. So there is an error. There's an error in this problem. The error is the correct answer is not here. The answer is going to be F, which is 0.032, right? That's kind of the level I'd like you guys at. I'd like you guys at that level where you can do this and say, oh, wait a minute, you did this wrong. You don't have the correct answer there. You need to fix it, right? Versus, well, I'll just pick the best, what's closest. A lot of people will pick what's closest rather than say, hey, wait a minute, there's a problem. Now, it's not just this test, but unfortunately our book has errors too. Like Ali, I think what number was that one?
51.
Yeah, 51. That's wrong. The answer in the book is wrong on that one. You should be able to go, well, it's just simple algebra, but obviously the book is wrong. That's not the only case. I have to check the new edition. In the 10th edition, there are a bunch of wrong answers in the solutions guide. Okay, and a lot of these the students pointed out to me. They said, I did this right. The answer in the book's wrong. Or maybe they said they did it right, but they did it wrong. They missed something. But I can help check that for them. This is why peer review's important. Even though this is a peer-reviewed textbook, sometimes the reviewers, referees, miss stuff. It could be, but I don't know what the book's answer said. Were all of them incorrect in 51? I didn't look at that carefully. So it could very well be, because when they changed it from the 10th edition to the 11th edition, they might have just forgotten to fix those answers there. But let's take a quick look here. Here's a reaction. 2NO plus O2 goes to 2NO2. A, K equals KP. Is that true or false? This is true. Did the book say false for this one? K is equal to KP is true. B, this is, yeah, this is true, but there was a wrong answer. The book said false, correct?
In the older edition of the book, it had delta G minus delta H.
Yeah, they probably just switched it or something. C, K is equal to E to the minus delta G naught R over RT. That's true. D looks true too. No problem with that. Okay, we're good. All right, what other questions do you guys have? Number 4. For the reaction below, which one has Kc equal to Kp, which is equal to Keq? Well, number 1, let's look. Is Keq equal to Kp or Kc? Look, what is Keq equal to for number 4A, for the first one? Kp, it's gas. Activities of solids are 1, it's just Kp. Is Kp equal to Kc? No. Kp and Kc are not equal. How can you tell?
Because, like you said, the opposite, AC equals KP and the change in the fluid gas is 0.
Yeah.
So
Delta N of gas. So delta N of gas is +1. We're going from no gas to 1 mole, so it's +1. So Kc and Kp aren't equal. The only time Kc and Kp are equal is when delta N of gas is 0. So let's look here. Delta N of gas is -1. We're going from 3 to 2. Here we're going from 1 to 1. Delta N of gas is 0. So Kc and Kp are equal. And then Keq is equal to Kp here. And so Keq equals Kp, and Kp and Kc are equal for C. D, there's no Kp for this. There's no gas, so Kp. All right, what else? You guys have questions with, or not sure of the answer for? All right, so again, for this one, there's no correct answer here. You just mark it. 0.032 is the correct answer. This is typo. Okay, are we good with this old exam? Your test is going to be similar to this in format, one page, some multiple choice, some calculations, maybe sometimes conceptual questions. If you have access to Mastering Chem and you want practice for multiple choice, there's some resources here in the study area. Practice quiz 1. So we have time. There aren't that many questions here. It's one chapter. Well, I already went through these. Okay, how, practice quiz 2 working. You know, what temperatures is the following process spontaneous? This is not asking, this reaction is spontaneous at high temperature, this reaction is spontaneous at all temperatures, this reaction is spontaneous at low temperatures, etc. This reaction cannot be made spontaneous at any temperature. This is like Hess's law, you know, use the delta G values. So if we add up the equations, we just add up the energies of delta G's. It's just like Hess's law. This is the same thing we're doing when we're doing delta G's of formation, except we're using formation reactions, so we don't have to write out the full reaction out like this. And so there's some resources for multiple choice here. Okay, any other questions? From homework or lecture?
Do you recommend having access to
If you already have it, yeah. If you don't, then it's expensive. So you don't have to have it. The multiple choice, the level of the multiple choice are on the easy side of the spectrum. Yeah. They have ratings from 1 to 4 for difficulty. So these would probably be a 2, you know, so in terms of difficulty. And there's nothing really that challenging. Okay, other?
66 from the homework.
66 from the homework? All right, how many people got number 66? Just curious. All right, use data from Appendix D to determine delta H, delta S, and delta G at 298 and K at 875 for the water-gas shift reaction used commercially to produce hydrogen. Assume that delta H and delta S are essentially unchanged at this temperature interval. There are lots of reactions available to produce hydrogen. This one's taking carbon monoxide and reacting with steam. This is going to form CO2 and hydrogen. Was there any problem calculating delta H, delta S, and delta G at 298? No? So the problem is, what is K at 875 for this? So if we want K at 875, what's the quickest? You know there are multiple ways of getting K. Do you know?
I did wrong.
Oh, do you know?
I used the delta G at 298.
Oh, okay. Yeah. All right. That's good. And so Mom was saying about this, e to the minus delta G naught at temperature T over RT. This temperature has to be 875 Kelvin. It has to match. And this temperature, of course, is 875 Kelvin. And so we need the delta G naught at 875. Well, we can figure out what the delta G naught at 875 is, you know, via separate calculation. Let's plug it in here, and we can solve for it. Okay, other questions? Number 77. All right, in an adiabatic process, there's no exchange of heat between the system and its surrounding. Of the quantities delta S the surroundings, and delta S the universe, which one must always be equal to 0 for a spontaneous adiabatic process? Okay, adiabatic, what does adiabatic mean? No heat exchange. So if we look at our system, can work be exchanged? Yes or no? Yeah. So we can't have any heat exchange, so no heat exchange. Of the following quantities, delta S of the surroundings, delta S of the universe. Well, what is delta S? What are they talking about? They must be talking about delta S of the system here. And so we're going to look at delta S of the system, delta S of the surroundings, and delta S of the universe. We don't know if work is done, expansion or contraction or whatever else. And we have to make it kind of an assumption for this particular one. But which one must always equal 0 for a spontaneous adiabatic process? So since no heat is dumped into the surroundings, you know, the surroundings are kind of isolated from this, then we would probably say that in other words, inside here can get quite hot, but it's not going to affect the outside. And so this is kind of isolated. If something's isolated here, is it going to affect the surroundings around it? No. And so we could say that the entropy doesn't change in the surroundings. So say it's the delta S of the surroundings must be 0.
Yeah, that's what I thought when I
Okay. Well, delta S of the universe has to be
The same as the surroundings?
no. Delta S of the universe is the surroundings plus the system.
Oh.
Delta S of the universe, we divide the universe into two pieces. We divide it into the system, and we divide it into the surroundings. This is right at the beginning of chapter 7. So separate it into two. And so if the system's 0, that means the surrounding, if the surrounding is 0, the system must go up. The entropy must go up. You know. This is something you never want to see. Like delta S if delta S is 0, then basically the system must be at equilibrium. There's no driving force for change. According to the second law of thermodynamics, right? So it's got to be at equilibrium. But this entropy stuff, confusing. Number 77. Okay, other questions? Number 77, I was thinking, I better not assign that to the one. For chapter 15, I'm going to take a different approach for this one. We're going to just look at the exercises for chapter 15. Unless, if some other questions come up for chapter 13, let me know. We'll come back to it. But let's take a look, because some of this stuff you probably already know. For example, Kc is the ratio of the product concentrations raised to the respective coefficients divided by the reactants. So this is a ratio of products to reactants here. And so if we look at the exercise of writing equilibrium constant expressions, this is just writing Kc expression for these. So what we have to do is we have to know nomenclature, and then we have to know how to balance equations. So we just first write out the balanced chemical equation, and then just take the ratio of product concentrations to reactant concentrations and raise those to their respective coefficients. And so that's number one. Number two, we do the same thing except for Kp. With KP, we don't use the concentrations, we use the partial pressures. That's 1 and 2. Let's take a look at 3. For 3, this is easier because they write out the balanced chemical equations, so we don't have to write out the formulas, we don't have to balance it, it's already there. So this is Kc, so this would be the concentration of NO2 squared divided by the concentration of NO squared divided by the concentration of O2. So we can go there for Kc. For 4, it's Kp, so it'd just be partial pressure of H2S squared times partial pressure of CH4 divided by the partial pressure of CS2 divided by the partial pressure of H2 to the 4th. And so, are those any, these should be easy, I think. What do you think? Easy? And so that's basically it for this, is writing out the expressions. The next thing is determining K's, you know. Okay, so here we can have Kp, Kc relationships, Kc, Kp kind of conversions. We have a formula for that. And then we shift. It's not just writing the K expression. Here we're trying to solve for K. And so this next series of problems from 11, 12, 13 is using Hess's law type approach. And that is, we want the K value for this equation here. But there are 2 ways we can get the K value for this. We can do it using the equations from thermodynamics. Using, we could solve for delta G here. From delta G we could get K. In this case we get Kp. We can convert the Kp to a Kc. And so we could use delta G's and all those equations, or we could do this experimentally. If we do this experimentally, we just measure the equilibrium concentrations or equilibrium pressures, whichever is easiest, and then get that ratio to get the K value. But there's an alternate way. The alternate way is by using this Hess's law type approach. And so let's try to get this by adding up these. And so we have some reference data here. So we know these 3 reactions, we know the Kc values for those 3. Let's try to add up these equations such that we get the desired one. Here. And so the approach I usually use in this is just look at the reactants. For example, I need 2 N2Os. Do any of these equations have N2O in them? The first equation has N2O, but it's on the wrong side, and it's only 1. And so what we have to do is we have to reverse this. If we reverse this reaction, that means we're swapping products for reactants. If we swap products for reactants, we have to flip the ratio. And so if we reverse this, we'll invert this. In Hess's law, if we reverse the equation, we just change the sign on delta H. We make it delta H negative rather than delta H positive. Here we invert. And so I'll do that. Okay, then I have to multiply by 2 because I need 2 nitrous oxides, N2Os. In Hess's law, when we multiply by 2, we double the energy. Here, we're doing it to the pressures. We're going to end up having to square that. And so the basic approach is I want 2 N2Os. I can get 2 N2Os by using the first equation. First, reverse it, multiply by 2. And so this is going to give me 2 N2s plus an O2. And then what I have to do to Kc1, I'm going to call that Kc1, is I have to invert it and then square it because I'm multiplying it by 2. And so this would be the K value for this equation. And so that gets me my 2 N2Os. The next thing I want are 3 O2s. I need 3 O2s, so I'm going to use this equation here. If I use this one, then I'll cancel out my N2Os. So let's use this one, and I'm going to go 3 O2s here. And get that. So I go for 3 O2s here. In order to do that, I'm multiplying this equation by 3. So I'm going to get 3 O2s plus 3 halves and N2. This is going to go to 3 NO2s. If I multiply that equation by 3, I have to cube the Kc value. So this would be Kc, the third one, Kc3 cubed. And then finally I want 2 N2O4s as products. I have N2O4 here as a reactant, so what I'm going to do is I'm going to reverse this equation and then multiply it by 2. So I'll invert that and square it. So if I reverse that, I'll go 4NO2s going to give me 2N2O4. And so I reversed it and multiplied it by 2. So I need to invert it and square it. And so this gives me all the K's for these here. And then with Hess's law, you just add them together. Hopefully everything cancels. So I get 2 N2O's, that's good. Plus this 3O2, that's good. Plus 3 halves N2. Let's see, does it cancel? Well, looking at this, I have 2 N2s here, I have 3 halves N2 here. So this 3 halves N2 will cancel out. This 1.5, so I'll have 1/2 N2 left over here. And 4 NO2s. I have 4 NO2s here, I got 3 NO2s there, so let's get rid of those. That gives me with 1 NO2, so I'll have an NO2 here. This is going to give me 1/2 N2 plus an O2. Oh, the O2s cancel, shoot. I got an O2 here, it's going to cancel out one of these. It's going to be 2. And then 2 N2O4s. Unfortunately, it didn't work out here. It didn't work out because I do have my 2 N2Os, and I don't have 3 O2s anymore. Sorry, I only have 2 O2s. Not enough. But I do have my 2 N2O4s. I need another O2 here. So if I need another O2 here, I got to add another O2. So let's go ahead and do that with the third equation here. I'm going to go with 1/2 N2 plus an O2. This is going to give me an NO2. And this is going to be KC3. So I'm going to add another O2 to bring it back up to 3. But look at now, the N2s cancel, and the NO2s cancel. And so what I end up with is 2 N2Os plus 3 O2s. This is going to give me 2 N2O4s. And the K value for this equation is going to equal this. It's going to be K, well, I'll just do it in line. It'll be 1 over KC1 squared times KC3 cubed times 1 over KC2 squared times KC3 from this last equation I had to add there. And so this is just like Hess's law, we just add the equations, but instead of adding the energies, we multiply the K's, and instead of multiplying the energies, we raise them to some power. Let me get it, and then we'll just plug in the numbers here. We should get the Kc for this particular reaction. So this just gives us another way of determining K values without actually having to do an experiment. Now, we could do an experiment. And so the next section here talks about experimental determination of equilibrium constant. If we want to determine the K value experimentally, all we have to do is measure the equilibrium concentrations or the equilibrium pressures. And so let's take a look at number 18 as an example of this. So what they do here at number 18 is they have a 0.500 liter flask, and it's filled with 1.00 grams of hydrogen and 1.06 grams of H2S, or gas. They let this react, and eventually it's going to equilibrate. You know, so at the end, at equilibrium, when there's no more reaction, no more change, this is going to be at 1670 Kelvin. What we see is that they have 9.65 times 10 to the minus 4, oh no, that's wrong, sorry, 8.00 times 10 to the minus 6 moles of S2 gas. And so what they want us to do is they're telling us the reaction that's taking place. So what they want us to do is figure out Kp for this reaction. So we got two hydrogen gas plus an S2 gas is in equilibrium with two H2S gas. So we can figure out what Kp is for this just by determining the equilibrium pressures. And so if I know the equilibrium pressures, the pressure of H2S at equilibrium squared, the pressure of H2 at equilibrium squared times the pressure of S2 at equilibrium to the first. And so I just need the equilibrium. So I set up an ICE table, ICE, and then just try to figure out what my equilibrium pressures are. But when I do this, you know, I notice I don't have pressures here. I have 1.00 grams of hydrogen. And then I have 1.06 grams initially of H2S. And then it looks like there's no S2 here to begin with. And so I have 0 grams of S2. Now, if I'm doing an ICE table, the ICE table, you only have 2 choices for the ICE table, pretty much. Well, 3 choices. Choice 1, you do it in molarity. Choice 2, you do it in bar. And then choice 3, you could do it in moles only if delta N of the reaction, not delta N of gas, but delta N of the reaction is 0. And so the safest thing is either do it in molarity, which we can do. We can figure out how many moles per liter, or we do it in pressure, bar, which we can because we can figure out how many bar this is. Those are the 2 safe ways of doing it. Or we could do it for moles if this is a special case. This is not a special case. We cannot do this in moles. And we certainly can't do it in grams. And since they're asking for Kp, we're going to do it in pressure, in terms of pressure. So in terms of pressure, let's figure out the pressure of the hydrogen. The pressure of the hydrogen, this is initial, you know, because it's not equilibrium. This is what we're starting with. And so the pressure of the hydrogen initial is equal to, well, what is it, nRT over V. And so I have 1.00 grams of hydrogen. And then let's convert it to moles. A mole of hydrogen weighs 2.016 grams. So I have moles of hydrogen times R. You know, I only know the atmosphere's R. I don't know the bar R. Well, if you don't know the bar R, do you guys have you memorized the R, the gas law constant, in terms of bar? Meters bar per mole Kelvin? No? They're very close, but they aren't the same. I don't memorize it because I already have another number memorized. I know that there are 1.01325 bar per atmosphere. And so the atmospheres cancel, it leaves us with bars. And so this would be the R constant in bars. Times T, which would be 298 Kelvin, divided by V, which is half a liter, 0.500 liters, 36 gigs. And so what's the pressure, the initial pressure of the hydrogen equal to? So 0.08206 times 1.01325 times 298 divided by 0.5. Oops, I miscalculated. Oops. No, I forgot. Divided by 2.016. $24.58. Is that what you guys get? Yeah. Okay. And so the initial here, we don't want the initial in grams. We want the initial in bar. The initial in bar is going to be 24.58 bar. And then for S2, we have none of it, so this is going to be 0 bar. For H2S, we'll do the same thing. Let me calculate the H2S. The mole amounts of H2S is 38. 06, 38, 09, 38, wait, 3808, sorry. So I have 1.06 grams of H2S divided by 3808 grams per mole times 0.08206 times 1.01325 times 298 divided by 0.5. 79. So this comes out to 1.379 bar. Is that what you guys get? Yes? No? So I have my initial. And then there's going to be a change in equilibrium. Well, equilibrium's already happened here. And at equilibrium, I have 8.00 mole times 10 to the minus 6 moles of S2. And so let's go ahead and calculate what the pressure is. 8 times 10 to the minus 6 is the moles times R, 0.08206 times the conversion to bar, 1.01325 times 298 divided by half a liter, 0.00396. 0.00396. Give myself one more digit, 3964 bar. So here, here's the change in S2. When I look at S2, this is plus 0.0003964 bar because I started off with 0 and then I added this much. So what happened was the reverse reaction took place. And so I'm going to call this plus Y. Some of the H2S that I had must have broken down into hydrogen and disulfur. If this is plus Y, then that means this must be plus 2Y because of the stoichiometry here. For every S2 I form 2 H2s. So this is going to be plus 2. So what I'll do is I'm going to double this here. $79.28. And so this should be plus 0.7928 bar. Mm-hmm.
Shouldn't Chem be minus Y and minus 2?
Normally, if the change would be minus if we're going left to right, but in this case, we got to be going right to left. We got to be going backwards because we have nothing here to react with, and so we're forming that. And so this is going to be minus 2Y on this side. And so this reaction actually goes in the reverse, based on what happened here. And so this is going to just be plus 0.0007928 bar. Assuming I did the calculations correctly, you would double check this. And so we can figure out, I call this Y because we can determine it. We didn't have to solve for Y other than just look at, we could solve it by sight here. And so we didn't have to plug it into the K. I call it Y when it's simple to figure out. I call it X when we have to plug it into K and do all the math to get it. Okay, William. And so I can figure out the equilibrium concentration here. This is going to be 24.5807928. The equilibrium pressure here is going to be this. The equilibrium pressure here, this is minus that. And so I'd have to calculate this. This is going to be 1.3789. Actually, that's 3 digits, sorry. 9 from 8. 9 from 7 is 2, 0. 7, 2. Something like this bar. And so I calculate the equilibrium pressures, and in fact, they only had to measure one because of stoichiometry, because I can't create or destroy atoms. The stoichiometric ratios have to hold. So we only had to measure one, and we could figure out the other two just based on the atom balance. Okay, once I have these equilibrium concentrations, I'll plug it in. And so this is an experimental determination of K. You know, they experimentally measured this value, the equilibrium value of S2, and based on the initial values, they were able to figure out all the other equilibrium values here and plug in to get the ratio. Uh-huh.
When calculating the pressure of hydrogen, you used 298 Kelvin. I'm confused why you didn't use 1670.
Because I made a mistake.
Okay.
That's why. I didn't use, I should have used 1670. And so, let me redo the calculations. I probably should just start it over, but I could just multiply it by a ratio. I could multiply by 1670 over 298, but I'm not. You know, yeah, so that was at 298. The temperature is at 1670. And so that means the pressure is equal to nRT over V. So for the hydrogen is 1.00 grams. I'll just set up the equation one more time. No wonder. I was thinking something's wrong because my numbers are different than this morning. All right, so essentially it's going to be 1670. All the changes are going to be off by that factor. So what I can do is I can just go here and correct these, the equilibrium ones. And so at equilibrium, fortunately I wrote a lot of digits here, so round off error won't be as significant, but it's going to be 24.5807928 times 1670 divided by 298. 137.75. And so the corrected one at 1670 Kelvin would be 137.75 at equilibrium. And then this is 0.000396.0003964 times 1670 divided by 298. Gives me a very small number. Just write in scientific notation. 7.96. 7.965 time. We go until what time? 2:25? Oh, we have lots of time. We have lots of time because I'm way ahead of the morning class now. The morning class had a lot more questions about chapter 13. And so this is as far as I made it in the morning class. Let me just redo the whole table, sorry. Okay, so I'm going to recalculate the initial pressure of hydrogen. And that's going to be 0.08206 divided by 2.016 times 1.01325 times 1670. Did I do, what did you guys get? did you get 137?
Yeah. I did.
137.75? 137.75 bar. Okay, this one's going to be 0 bar. And then the H2S. The H2S is going to be 1.06 grams. And the molar mass of H2S is 32 plus 2 hydrogens. Maybe I got the molar mass in the morning wrong. 34.067808 grams. And the rest is the same. The 1.06 divided by 34.08 times 0.08206 times 1.01325 times 1670 divided by 0.5, 8.63. And so for the H2S initial, I get 8.637 bar. Carry one extra. And then for the S2 at equilibrium, this is at equilibrium, so it's 8 times 10 to the minus 6 moles. 8 times 10 to the minus 6 moles times 0.08206 times 1.01325 times 1670 divided by 0.5. Yeah, this is what I got this one. 0.00221. I'll just carry one extra digit for this one. Bar. All right, so this is plus y, and so 0 plus y equals 0.00221 bar, which means this is going to be plus 2y. And so it's going to be 137.75 plus 2 times that value there. So times 2 plus 137.75 gives me 137.75 bar. It's a very small number. And then this is going to be minus 2y. And so 8.637 can do it. 8.637 minus 0.00221 equals 8.634 bar. So we didn't lose much. So now, once I have the equilibrium, I figured out the equilibrium based on this one experimental measurement. This one experimental measurement allowed us to calculate the other two. And so these weren't actually measured. Just based on the stoichiometry, you can figure out what those are. And so if we can plug this into our Kp expression, it's going to be 8.634 squared divided by 137.75 squared divided by 0.00221. And that should be our Kp value. All right, so once you punch that out, then we get the Kp. And so these are the kind of the same thing. Here we have the reaction PCl5 to PCl3 plus Cl2. They measure the quantity of Cl2 present at equilibrium. And so we have the equilibrium amount of Cl2. This is in moles, so what do we have to do? If it's in moles in the ice table, we need, not moles, we need molarity. And so we got to convert this into moles per liter. We have the liters here, so we can do that. So convert that into molarity. So we have the equilibrium molarity of Cl2. But what about the equilibrium molarity of PCl3 and PCl5? Where do we get that? Well, they don't tell us that, but based on this, they said that this much was introduced into a flask. That means there was 0 and 0 here. So we know what the initial conditions are. This molarity, once I can divide it by that many liters, and 0 and 0 led to this molarity of Cl2 at the end, so we can figure out what y is. So I'd call this a y problem, not an x problem. The same thing with 19. They give us enough information to calculate y. And so these are all the same. And so 20, 21, and 22 are just figuring out what y is here. Okay, then we go into using k's. When we use k's, then we want to do our Chem 1b stoichiometry. And so these are the equilibrium relationships here. Some of these are calculating the k values. Some of these are a little bit different. Like number 23 is a little bit different than what you'd normally do in a equilibrium type calculation. You know, sometimes the answer to a problem isn't a specific number. You know, sometimes when somebody asks you, you know, what's the answer to this, sometimes what you do is you give them a range, you know. This would be the minimum value, this would be the maximum value. Like, what's the range of phosphoric acid you might expect in Coca-Cola? Well, I'd expect this to be the minimum, this to be the maximum, somewhere in that range. Sometimes when you answer a question, they don't give you all the variables. Like, for example, if you were to do an ideal gas law problem, you need pressure, volume, moles, and temperature. But what if they only gave you 2 of the 4 variables? Now, if they gave you 2 of the 4 variables, you might say, well, you know what, I can't solve it. But that's not right. You know, that's not the right answer. That's not the answer that they're looking for. They're looking for an equation, you know. Yeah, so for example, if they were to give you 2 of the 4 variables, you know, let's say we know the pressure and the volume, but we don't know N and T, right? And so we could solve, for example, we could solve T, you know, T for this is going to be equal to some constant, right, divided by N. And so they show, you know, how things vary depending on some variable. And so number 23 is that sort of question. In number 23, equilibrium is established at 1,000 Kelvin, where Kc is 281. And so here for number 23, the way we break it down is we need Kc. This is Kc at 1,000 Kelvin. And Kc at 1,000 Kelvin is 281. And so it's slightly unfavorable there. For the reaction 2SO2 plus O2 yields 2SO3. And so this is Kc, so looking at that equation, I know that this is going to equal SO3 squared divided by the SO2 squared divided by the O2, since it's a Kc. We're dealing with concentrations here. These have got to be the equilibrium concentrations. So one thing we can do is we can measure the equilibrium concentrations and get this. But we already have this number, so we don't need to determine what K value is. They tell us the equilibrium amount of O2 in a 0.185 liter flask is 0.00247 moles. And so the equilibrium concentration of O2 is 0.00247 moles per 0.185 liters. And so we can figure out the molarity of this pretty easily. So figuring out the molarity, we get 0.00247 divided by 0.185 is 0.01335 molar. Well, I have this, right? But that leaves 2 unknowns. And so if I know K and I know O2, I have 2 unknowns here. And so I'm not going to be able to solve this to a unique answer if I have 2 unknowns in one equation. So there are different things I can assume. So for example, I can assume SO3 is this concentration. What are the ranges of SO2? Or I can assume SO2 is this concentration. What are the ranges of SO3 I'd expect? Or I could solve this to an alternate equation. What is the ratio of SO2 to SO3 in this equilibrium mixture? So I could try to figure out what the ratio of SO2 to SO3 is. The ratio of SO2 to SO3 is flipped here. Do you see that? And so what I'll do is I'm going to solve this here for SO3 squared, SO2 squared is going to equal 281 times the O2 concentration, which we already have. And so we know that the O2 concentration is 0.01335. Okay, multiply these out, and then what I'm going to do is I'm going to flip this and take the square root. And so that the SO2 concentration in equilibrium over the SO3 concentration in equilibrium is going to be 1 over this, the square root of that. So what's 281 times 0.01335? So 281 times 0.01335, 3.751. And so the ratio is going to be 0.516. So it's 0.516 to 1, basically. Or, you know, if you want to do it, it's like a 1 to 2 ratio. All right, so sometimes we do problems like that. Other times it's just straightforward, like stoichiometry type calculation. So let's take a look at some of the other problems in here. For the dissociation of iodine at about 1200 degrees C, so iodine goes to 2 iodine atoms. Kc is 1.1 times 10 minus 2. What volume flask should we use if we want 0.37 moles of iodine present for every 1.00 moles of iodine at equilibrium? And so, you know what this sounds like? This sounds like we're trying to target the amount of reaction that takes place, right? We want a certain amount of iodine to react. In fact, what they're saying is that for every 1 mole of iodine at equilibrium, they want 0.37 moles of iodine present. And so that means we're targeting a specific K value. It's like what we did earlier, like when we wanted 99.99% reaction. You know, we'll get the same kind of deal here. And so in this case, for all these problems, except for number 23 here, but for all these problems, if you don't know where to start, we always start at the same place. We always start with the ICE table. And when we get the ICE table, we just try to figure out as much of the entries as possible. And so we have ICE here. ICE, they're saying, okay, are they giving us a KP or KC? They're giving us a KC for this, and they tell us the KC value is 1.1 times 10 to the minus 2. That's the KC here. But what is the temperature of this? The temperature is 1200 degrees C for this. Here. 1200 degrees C. Now, you know, what volume flash should we use? Well, if we're dealing with a KC, that's molarities. And this is good, excuse me, this is going to be the molarity of iodine squared at equilibrium divided by the molarity of I2. Atomic iodine versus molecular iodine, or diatomic iodine, at equilibrium here. But when we go to the ICE table here, all we have is this. They want, okay, so our target here is this. We want 0.37 moles of atomic iodine. So we want 0.37 moles of atomic iodine for every 1.00 moles of I2, right? But the problem is an ICE table like this, we can't leave it in moles. The only time we can leave it in moles is when the total moles on the left is equal to the total moles on the right. The reason for that, do you know the reason for that? We can only use moles when this happens, when we have like an A plus B yields C plus D. If we have an A plus B yields C plus D, then we got the concentration of C. The concentration of C is the moles of C over the volume. the concentration of D is moles of D over volume. The concentration of A, moles A over volume. And B would be moles B over volume. Do you see the volumes cancel out? I got volume squared here and the denominator, volume squared here. They cancel out. However, if I did this, if I went from 2 moles to 1 mole, then I get rid of this. Now do the volumes cancel out? No, the volumes don't cancel out because I got volume squared here and volumes to the first here. So the only time I can use moles is if I have a scenario where the total moles on the left is equal to the total moles. This is not moles of gas like delta N gas. So in this case, I need the volume, otherwise this does not work here. And so I'm thinking, well, I already know what the equilibrium should be. It should be this, and it's got to be this ratio here. And so let's just plug this in here. And these are kind of oddball problems here because it turns out, you know, it's going to be a concentration ratio. And so I'm going to figure out what the volumes are going to be for this. So what I'm going to get here for the iodine is 0.37, you know, kind of moles. The units don't always work out, but this is going to be over V squared. Actually, the whole thing's squared. Over 1.00 over V. Let's get rid of the moles because, you know, these are activities, but, you know, now that we've got the volume, we've got to solve for the volume. And then we just solve for V. And so this is another unusual problem. Number 23 and number 24 are not your typical problem. You know, your typical problem is figuring out the what the equilibrium mixture is going to be at the end using K values. Well, let's take a look at number 25. Number 25, in the Oswald process for oxidizing ammonia, a variety of products is possible. You know, when we oxidize, it depends on, you know, a variety of products is always possible in redox. Do you guys remember, if we want to get into advanced stuff, then, you know, the Chern method is not perfect. Let's see if it's still here, if they wipe it. If we want to get into advanced stuff, then we have this kind of diagram that we need to look at. This type of diagram here shows us, you know, all the products. So for example, if we take manganese and we oxidize manganese metal, it depends on how powerful an oxidizer we use. So for example, if we use mild oxidizing conditions, we'll mildly oxidize it. So we might go from manganese to manganese 2+. That's with a mild oxidizer. However, if we use a powerful oxidizer, what would happen? If we use a powerful oxidizer, we take manganese and go all the way to manganese +7. Can we go to manganese +8? Does that exist? No, and so it depends, and these numbers tell us something, and it depends on the conditions being concentration, strength of oxidizer, etc. We don't get into this kind of detail. So for example, when we do something like this, let's say we're taking manganese 2+ and oxidizing manganese 2+, if we go back and look at the redox chart here for manganese 2+, if we take manganese 2+ and oxidize it, are we going to manganese 4, manganese 5? Where are we going to? We're going to take it all the way to manganese 7 because it just makes sense. You want to do when you do reactions. It's like just like when you're combusting. When you're combusting methane, we can form a lot of things like soot and carbon monoxide. But when you write out the equation for combustion of methane, do you write it to soot and carbon monoxide? No. And so let me give you a hint for the quiz that we had yesterday. This is the hint for the quiz. The first hint for the quiz goes back to my story about Joshua Tree. Does anybody remember the Joshua Tree story, the 99 cent?
That your alcohol
Yeah, the ethanol. This is something you learn in organic chemistry. When you go to organic chemistry, it depends. For example, here, it depends on how strongly ethanol is oxidized. In your body, it goes in steps. We don't go straight to the end. And so what we can do here is, this is the symbol for oxidation in organic, and we do mild. We do mild oxidizing conditions. This just means oxidizing. Oxidizer. So you pick an oxidizer. If you pick a powerful oxidizer, it could do one thing. It could take it all the way. If you pick a mild oxidizer, it takes it part of the way. And so normally ethanol is oxidized to something called acetaldehyde, which looks like that. I saw people, actually it wasn't this class. I saw people Googled this. And some people put acetaldehyde. But that's very mild. A little bit more rigorous, you could produce acetic acid. This is what happened to me. What happened to me was a little bit of oxygen got through the cork and started to oxidize the ethanol. Fortunately, it didn't oxidize it to acetaldehyde. Acetaldehyde would have tasted much worse, probably. I don't know. They probably taste equally as bad. Probably there was a lot of acetaldehyde in there, along with acetic acid. And so I think, Eric, you put acetic acid, is that right?
Yeah.
Well, that's not enough. That's not enough because that's very mild. That's a tiny bit of oxygen leaking in there. And oxygen, we're using a much more powerful oxidizer than oxygen. In terms of strength, oxygen versus dichromate, dichromate's a beast compared to oxygen. And so what happens is, something so powerful as dichromate is going to take this all the way. Well, what's the next step? Maybe we stop at soot. Do you want to form soot, carbon particles? No, we're going to take it all the way to carbon monoxide. Do we take it to carbon monoxide? Well, it depends on the conditions, right? We could very well take it to carbon monoxide, but considering how powerful dichromate is, you'd expect it to go all the way to carbon pentoxide. Why stop at carbon dioxide? Why not go all the way to carbon pentoxide? Because carbon pentoxide doesn't exist. It goes to carbon dioxide, something that powerful. And when you're looking at these oxidizers, that's a powerful oxidizer right there, dichromate. Oxygen's up there too, but will oxygen burn ethanol to CO2 easily? Or does oxygen only burn ethanol to soot or carbon monoxide or vinegar? When you burn ethanol, do you get acetic acid? No, it burns it all the way to carbon dioxide. So this is the type of stuff. The question from the quiz. Well, anyway, going back to this, let me just quickly go back to this. We're just about out of time here. Is this. The same thing happens in cars. In cars, we burn nitrogen. We burn nitrogen because in cars, in automobiles, does nitrogen burn very easily? No. Nitrogen is, if there's a bad reducer, nitrogen is it. Nitrogen is an awful reducer. And therefore, in cars, we call it NOx. We call it NOx because we get a whole mixture of different things depending on how extreme the conditions were. And so these are the NOx, N2O, NO, NO2. If we're truly extreme, we're going to go all the way to NO2, which is pretty much completely combusted nitrogen. Right? And so this is this is though, we're not burning nitrogen though, we're burning ammonia. And burning ammonia, well, it depends on the conditions, so we can get a mix of products there. But sometimes we just make an assumption. The assumption we make is we go all the way. That's what I told you for double replacement. So anyway, we'll continue looking at these as we go along.
Chris, we got a pre-lab tomorrow?
No pre-lab. You don't have to prep. I'm going to talk about Le Chateliers at the beginning.
Or you think lab, then
What's that?
less than lab.
We're going to do lab and then test.
So I'll do this.